So how many of you guys honestly thought I was going to let that go and that was going to be the end of the pulse duration modulation experiment? We built the little transmitter, we made a few contacts, we got some critique. It is what it is. After all, that basic circuit was developed in the 90s. It never really went anywhere. You never see anything developed from that schematic. We start to get into modular PDM, where people are building transmitters in sections. You start to see kits and boards become available for the power amplifier stages, for the pulse duration, pulse width modulators, and it becomes kind of a cookie cutter formula type thing to do PDM. You can even buy complete modules tested and ready to go. So we take our first principles transmitter and we realize that we are not getting very good talk power. The RF power is very low, right? And let's see what we can do to try to pep it up a little bit. The first thing, and this has been suggested by many of the commenters and also by the community that I was trying to talk to that have been doing PDM for many, many years, you need to get more modulation density. You need to get more upward modulation. Have you thought of doing some negative peak limiting and possibly increasing your modulation from 100% to maybe 125% or 130 or 140% upward modulation? So that means we need something called a speech processor. Now I've got a little teaser here. This is an Electro-Voice 638. This is a classic microphone of the late 50s that was used with many of the early single sideband transmitters. And maybe this is not appropriate for high fidelity type PDM, but it's certainly appropriate for good talk power and good intelligibility. Of course, it doesn't have the frequency response that we had with our fantastic Electret-based microphone developed in the last video series. But I've got a box here that I'm putting together. I'm calling it a speech processor. It can accept either an Electret-powered microphone or dynamic microphones like this one. So I've got two different inputs. Also, it's going to be available to change the polarity of your speech. What is polarity when it comes to speech? We're going to cover that in this video. There's going to be some clipping involved, and by clipping I mean negative peak clipping, and we're going to learn about soft clipping versus hard clipping. And also we're going to be doing a little bit of equalization, that is fixing the audio response so that it works better with the transmitter. We know that the transmitter doesn't seem to have a flat audio response to the human voice. Let's fix that with an equalizer. So this is all about speech processing. Welcome to Speech Processing, Video 1. There's no doubt we need an audio amplification system for our microphone that's going to allow us to both adjust the tone or the equalization of the audio, as well as to perform some negative peak clipping so that we can modulate upward and not overmodulate below zero, causing distortion. On top of that, we would like to have a fairly low noise amplifier and bring the gain up a little bit because we were a little shy on gain. Now I'm still working with the ATX power supply as my major source of parts. And there's a lot of bipolar transistors. I've pulled off some of these ATX power supplies. And they're all over the place, but there seems to be several that are used over and over again. The 2SC945 seems to be used a lot. It's a general purpose transistor, low noise, has a pretty high gain bandwidth, has a pretty high FT, and they're all over these ATX supplies. It's a wonderful NPN transistor. The only thing you have to be careful of with this transistor is the pinout is different than the 2222 or the 3904 that you're used to. So with the transistor looking at you, it's emitter, collector, base. So that'll mess you up. But I want to use these transistors out of the ATX power supply to see if I can do all of this discrete. I was thinking of using an op amp at the end. We'll see if I actually use an op amp or not. But I want to be able to do clipping. I want to be able to do phase reversal to get my voice in phase. And I need a little bit of gain and a little bit of shaping. So I have to start this discussion on audio processing, low-level speech processing, microphone processing with a disclaimer. A lot of hams have come out of the broadcast industry, whether they were part-time DJs in college or they were the main engineer at 30 Rock for 30 years. And there's a lot of opinions, a lot of audio expertise, and a lot of experience with broadcast quality type equipment as applied to ham radio AM operation. So this is not that. We're just trying to make a very simple speech processor for our microphone. And along the way, I expect a lot of comments on some of the circuitry. So, first of all, let's look at some basic low-level speech processing techniques. And the type that we're actually building is this first type, which is conventional clipping. We have a preamplifier that brings the microphone up to a level that's what we would consider to be kind of line level, a safe level of 100 millivolts, a couple hundred millivolts RMS of audio. Then we need to do a polarity swap, and we'll go through this. The human speech usually has one direction that it goes. When you put the speech into the microphone, it will be an upward type waveform or a downward type waveform. We need to do a correction. Then equalization, and EQ is simply taking care of the highs and the lows and the mid-range. And then we usually have some type of negative peak clipper that takes care of the low swinging excursions that might cause us to overmodulate and go through the zero in our AM waveform, thus causing distortion, interference, all kinds of nasty things that cause people to complain about AM operation. And finally, there's usually a low-pass filter tacked on to take care of any nasties that are produced by the clipper. The second style of speech processing is called automatic level control or automatic gain control. This is very popular. Many of the broadcast type processors use this technique. There's normally some sampling done at the end. It's fed back to a compressor or a low-level amplifier stage, and it tends to reduce the dynamic range of the speech so that it better fits into the modulation envelope. And this gives you more talk power. Companding is another technique. Usually this is done in the radio circuit. You take the compressed audio and you modulate the radio with it, and then at the other end, when you do the demodulation, you do an expand function and bring it back to normal speech. If you were to use this on your ham radio, it would sound pretty funny. Now here's the most popular one today. It's called DSP processing. We basically do an analog to digital conversion of the speech. We do DSP processing, and then we do a digital to analog conversion back to baseband, filter it, and send it into the radio. Probably 99% of the speech processors today and going forward will use this technique rather than the analog techniques that we're talking about here. The requirement to limit dynamic range or to level speech in a circuit came from the military in the 40s when they wanted to reduce the problem with intelligibility over long circuits and complicated circuits with many different types of analog signals from receivers, from people speaking, from intercoms, and so on. So the military developed compressors in the 1940s. Broadcasters had been experimenting with them in the 30s, but a lot of it came out of this early military development. Companies like Gates developed compressors that are used in many radio stations. And these types of compressors are in great demand. As retired from radio stations, hams would love to get their hands on some of these units. Now, these units are really line level units. That is, you put in a 600 ohm signal and you get out a 600 ohm signal at line level. Look at how simple this Gates stay level diagram is. They take a little bit of the output and they detect it, turn it into a DC bias that is used to control an input stage, level controlled stage. It's a very simple closed loop feedback system that allows you to set levels and keep them constant at line level. How could something so simple as this be so desirable by ham radio operators? Here's another Gates. Now, these are so popular in the audio industry that people are starting to knock them off and build copies of some of these old circuits, and of course do innovations and improvements. There's some other companies, of course, that made boxes that you'll find that are very desirable. A lot of things coming out. I'm not going to, go down this path too far, but you can see that there's a lot of boxes out in the world that you're going to find at your ham radio flea market, and they're interesting to experiment with. These could be useful to you in your station. Now, Analog Devices has developed some interesting AGC chips that are now being applied to small AGC modules that you can buy to do speech processing. I can tell you that I've worked for companies that have made small processor modules like this. Some of them developed on hybrids back in the 70s for all kinds of speech processing. Here is the classic feedback style compressor. You have a op amp, you're amplifying the audio and it goes out to your radio, but first you detect it, send it back to an amplifier that controls a field effect device that's a variable resistor in effect. So you have a variable gain amplifier. This closed loop system is a typical automatic gain control system that's used today. So let's go into our circuit, and here is the preamplifier circuit that I developed based on the Elliott Sound Products design. It's a cascaded NPN type low noise. It uses all metal film resistors for low noise, and it will work very well with low impedance microphones like dynamic or electret microphones. The electret is a high impedance device, but it has an onboard follower that turns it into a low impedance output. So the electret, even though it is a high Z type microphone, it is a low Z in this application. The gain control is here. You can see this is nothing but a very simple 2-transistor AC coupled op amp. Now, I've tacked on something called a phase reversal switch. Now, why do you need phase reversal? The human voice is not a constant sine wave. It doesn't have as much upswing as it has downswing. It doesn't have as much downswing as it has upswing. It's all over the place. So sometimes you need to set the polarity of the speech for input into the modulator. And I'm doing this with a very simple phase splitter. Again, everything's running on 12 to 15 volts. Make sure you do your biasing properly to keep these points at a good place to produce the maximum amplitude. If done right, you should be able to get 4 or 5 volts peak to peak out of either of these phase reversal outputs. If you do it wrong, you'll get 2 volts out of one and 6 volts out of the other, and so on. Now I've tacked on equalization. With some EQ, we can correct the lows and the highs in the speech. We've done the preamplification to a safe level. We've done the polarity swap with a phase splitter. We've got a little bit of buffer gain here, and this was just because I wasn't sure how much gain I needed, so I put this in here so I could adjust gain last minute. And then we have a conventional bass treble equalization amplifier. Now, if you were clever, you could probably dispose of 2 of these transistors and still get good performance. I kind of overdid it with this circuit. I used 5 transistors when you probably could have used 3. So finally, at the end, not at the beginning, not in the middle, this is where you put your negative peak clipper. You want it as far towards the end as possible. As a matter of fact, a lot of people like to do negative peak clipping right at the modulator stage, not low level like we're trying to do. So this negative peak clipper uses a soft clipper system with 2 diodes. It allows the positives to come against the diode, which is a backward bias diode, so there's no attenuation, but the negative cycle is attenuated and clipped at the level of the diode's forward conduction. So if you want a lot of clipping, you would use Schottkys here, like a BAT 85. If you want medium clipping, you can use some 1N914s or 1N4148s. Again, I had to build up enough voltage that I could get the clipper to even operate. By that time, it was way above what I wanted to put out, so I had to put a gain pot at the end, a little trim pot, to bring this in the same level as the output of the main speech processing sections. So another point of contention, have you guys noticed how the price of project boxes has gone through the roof? The project box that used to be $12.95 is now $24.95. And the $15.95 box is now in the $30 range. I have to say, guilty. I think that the Microwave 1 channel has caused you guys to go crazy and start to build so many projects that you're driving the market. Cool it, guys. Some of these boxes are getting pretty expensive. At least that's my theory, and I'm sticking with it. Injecting a signal into the preamplifier, the 2-transistor preamplifier, and then into the single transistor phase splitter. And looking at it on the scope, we can see that we get a perfect 180-degree phase swap between the 2 oscilloscope channels. So our phase splitter is allowing us to select either one polarity or the other polarity. So I finally got sick of that oscilloscope, and the thing just wouldn't focus, So I did have to take it all apart, and I finally found the astigmatism potentiometer. And I thought while I was at it, I might as well go through a whole calibration on the scope. I'm not going to bore you guys with that, but so even a poor old analog scope like this BK deserves to have a calibration now and then. And when do we fix these things? When they finally drive us completely nuts and we throw it in the trash, or we dig into the manual and see if we can fix it or calibrate it. So, let's talk about polarity of speech. Now, some of those guys were complaining that I didn't have a lot of positive modulation. Now, this is an ordinary hand microphone. It's a dynamic mic. Has an impedance of a few hundred ohms. I'm just going to put it straight into the scope. 1, 2, 3, 4, 5. Hello? 1, 2, 3, 4, 5. I think you can plainly see that this microphone has a positive polarity to my voice. It is correct to my voice. Now, if I was to put this into an inverting amplifier it would flip this waveform, and what you would see is a downward trend in the modulation. We want to be able to always put it back into this normal position. And you don't know, you're going through many stages, a lot of phase shift, a lot of 180 flips. So the only way to solve this is to put a method of changing the polarity by 180 degrees, and that means we're going to need some type of phase splitter and a switch. So in order to make the negative peak clipper work, we have to have enough amplitude to turn the diodes on, which means we're going to need a couple volts of audio. Now the preamp can almost do that. It's lacking a little bit of gain. And the other problem we have is the phase splitter that we selected, being a transistor type, is sharing the load of the 12 volts on the circuit. And I'd rather not run everything at full output, full gain. So I want to add one more stage. So we have plenty of these transistors that we're getting off the ATX power supplies. So I'm going to add one more stage with a gain of about 20. That's easy to do with an H-bias transistor, something between 20 and 25 dB of gain. That will allow us to run the lower level stages in the, in the 50 to 100 millivolt region rather than way up at full gain. So I'm looking at the output now, and this is with the gain pot on the preamp only at about a third. If I flip the switch, okay, I flip the switch, and now, as you can see, my voice is going down instead of up. That's why we have the phase reversal switch. We definitely want the positive peaks to go to the modulator. Okay, so this is a single diode clipper. It really doesn't look too bad. The diode seems to be turning on okay. I'm putting in a reasonable signal, about 1 kilohertz. I guess it's 900 hertz. Okay, there's 1 kilohertz. And now I'm going to add the softening resistor. Okay, I'm going to add this resistor right here. Okay, I'm going to put that in. This is going to allow the diode to turn on a little softer, and you can see how that's rounded the bottom. Okay, so now we've got a second section of rounding, and we end up with a little sharper clipping, but again the bottom is rounded out, and that's what I'm going to go with, is a 2-section softened clipper. So let's look at the waveform with the clipper in line. 1, 2. At low level it's very linear. But once you start talking, oh, 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 you can see lots of upward, hello, hello, hello. But the lows are attenuated. The low excursions are attenuated. Hello, 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 lots of upward. But the lows are truncated in such a way that it's not sharp, but you can see it's compressed. Now let's take a look at the compression from the clipper with the sine wave. You can see it's starting to come in a little bit. Okay, it's allowing the unmolested upward swing, but it is truncating the bottom. Okay, I've got a net going in the background, but let's take a look at the speech processor with a 1 kilohertz sine wave. Now let's look at putting in the clipper, and as you can see with the clipper, we definitely are lopping off some of the negative peak. Now if you wanted a more drastic cut, instead of using silicon diodes, you'd use Schottky diodes, and that would bring this up, of course, a little bit higher on the waveform. I just wanted to show you what it's like when you cut in the clipper. Now we can set the clip level. You can set it low enough that you can get this thing linear. You want to set that clipper and leave it, and then do all the adjustment with the final gain control. Okay, let's look at this waveform. I've got the microphone now. I'm talking into the mic. I think you can see that most of my energy is going north. The microphone is properly polarized to my voice. If I flip it with the phase switch, 1, 2, 1, 2, 3, 4, 5, you can clearly see that the peaks are now going the wrong direction. So next, let's look at the clipper. Let's put the clipper in. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. As you can see, it's dynamically cutting the negative peaks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Take the clipper out. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You can see the negative excursions are going a lot lower. 1, 2, 3, 4, 5. And we put the clipper back in. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We can adjust the severity of the clipping with this control and the overall output of the speech processor with that control. So I'm not going to get overly excited about this box. It's a speech processor. Basically, we have enough modulation that we can certainly get, high enough modulation. We can increase it, hit the 0, and so on. But I wanted to show you the little box. First of all, in the back I have some equalization. I can increase the highs. Testing, testing. Hello, more highs. Okay, I can increase the lows. Hello, 1, 2, 1, 2, 1, 2, 1, 2. I can play with the audio response now. I also have the phase reversal switch. 1, 2, 3, 4, 5. This is one way, and 1, 2, 3, 4, 5 the other way with more energy. And then I have the clipper. I can put the clipper in. The clipper's in now, testing. Testing, 1, 2, 3, 4, 5. I can control the clip level here, and I can control the main gain for the whole thing here. But now I can, when people give me complaints about the audio, I can at least do something. I can adjust it on the fly, and we can have all kinds of fun. Hello, is this thing on? Oh man, we covered a lot of material with speech processing in this video, and I hope this encourages you to start working with different kinds of microphones, tailoring your speech to give upward modulation, and putting more talk power out on the air.